Welcome to the live interactive session for the course Surface Water Hydrology being taken by Professor Dr. Rajiv Mathi from the Department of Civil Engineering, IIT Kharagpur. I am the teaching assistant Aman Srivastava, and today in this session we are going to solve some numerical problems on hydrologic design concepts. In this lecture we will be focusing primarily on four types of numerical problems, namely for plotting position formula, log normal distribution and Gumbel distribution. So let us start solving problem on plotting position formula. Let me read the first problem for you. Find the probability that a 50-year flood may not occur at all during the 50-year life of a project. So it's a very straightforward question where we need to find out the probability that a 50-year flood may not occur at all given the lifetime of a project, which is 50 years here. So let us see how we can utilize this information to actually find out the probability. So first of all, the equation that we are required to use after reading this problem is this one, P0n, which is equal to 1 minus P whole power n, where this P is the exceedance probability, which can be rewritten as 1 by T. Here T is the return period, which is provided in the problem, that is 50 year. So now if we substitute the values provided in the problem, that is T and N is the lifetime of the project, which is 50 years again provided to us. Then this 50 and 50, if we substitute and solve, we get the probability that the given 50-year flood may not occur at all. May not occur here means 0, which is placed here, that is the R is equal to 0 here. So we solve by substituting the values of T and N in this equation, we get the final probability as 0.3642, which is the final response to this question. I hope you were able to understand this problem and must have understood how we can actually utilize this plotting position formula to arrive at these kind of probabilities. Thank you. Moving ahead, let's solve another problem on log normal distribution. Suppose X indicates one hydrologic variable following log normal distribution with mean 415 meter cube per second and standard deviation 100 meter cube per second. Now if Y denotes a log transformed series of X, that is Y is equal to ln X, then find approximately the mean and standard deviation of Y. So initially the mean and standard deviation which has been provided is in the series of log normal distribution is following the log normal distribution, while the new mean and standard deviation that we need to find out is the log transformed series of X, which is Y. So let us find out the log transformed mean and log transformed standard deviation of Y. In this regard, first of all, we need to find out the relationship between the mean and standard deviation. For that, we have these two equations, which is written in terms of original variable X, which is Y bar is equal to half ln X bar whole square divided by CV square plus 1, where CV is nothing but it's a coefficient of variation. And likewise, we can also find out the log transformed standard deviation for the variable Y as under root ln bracket CV square plus 1. Okay, and now we know that the X bar which is already provided in the problem is 415 meter cube per second, and the standard deviation around X, which is the original standard deviation, is also provided in the problem, which is 100 meter cube per second. Now the formula to arrive at CV is the coefficient of variation is given as the ratio of standard deviation around X by mean at X. So it comes as 100 divided by 415, which is equal to 0.24 is the coefficient of variation. So this is what we have obtained from step 1, that is X bar as X and CV. Moving ahead, let us now find out the mean and standard deviation of Y, which is what is the basic purpose of this problem. Now we are having the value of X bar as X and CV. So now we can substitute these values in the main equation, that is Y bar is equal to half ln X bar whole square divided by CV square plus 1. So here X bar is 415 whole square, CV is 0.24, substituted likewise, and we got 6 as the final response, which is the Y bar. So the mean of Y, which is a log transformed variable Y, is 6, and likewise we can obtain the standard deviation of Y by substituting the value of CV, which is 0.24 in this equation, and we get 0.24 as the standard deviation of Y. So this is how we can actually solve the problem of on log normal distribution. Now let's move ahead and solve the third problem for the today's series on normal distribution. Let me read the problem. Consider 50-year data of annual maximum 24-hour rainfall at a particular place following a normal distribution with a mean of 101 mm and standard deviation of 60 mm. Determine the magnitude of annual maximum rainfall with a return period of 20 years. So our whole objective in this problem is to find out the magnitude of annual maximum rainfall, and the return period is provided to us. Apart from this, other data is also provided, such as the mean and standard deviation of the normal distribution, and the data length is given to us, which is 50 year, and the duration for which the rainfall data has been obtained is 24-hour rainfall at a particular place. So let us see how we can actually utilize the information given. In the step 1, we look forward to find out what are the given values. So here the mean and standard deviation is provided to us, which is 101 mm and 60 mm respectively. So using this information, we can actually arrive at probability of accidents, which is P. So how to arrive at return period T, 20 years, is given to us. So here for x greater than x20, 1 by t is 1 by 20 is equal to 0.05 is the probability of accidents P. So what is the non-probability of accidents? That is 1 minus P. So 1 minus 0.05, which provides 0.95, that is also Q. Now we can use the standard normal table to find out the frequency factor K. So how to arrive at? So currently we are having 0.95 as the non-probability of accidents, and we can locate this 0.95 here. So corresponding to 0.95, the value of Z or the frequency factor K that we get is 1.6, and here we can say that this 0.9505 and 0.9495. So our value is between these two, within these two columns. So the value of K will be 1.645. So this is what has been shown here, that from the normal distribution table, the corresponding value, that is Z, which is frequency factor K, is 1.645. So in the step 4, we can actually find out the magnitude of the annual maximum rainfall for the log transformed variable x. So here x20 is x bar plus k s x. So here we now know x bar is 101 mm, which is already given the problem. K, just now we have obtained 1.645, and the standard deviation around x, which is also provided in the problem, which is 60. So substituting all these values in this equation, we obtained the x20, that is the log transformed variable x, is 200 mm, which is what the magnitude of the annual maximum rainfall that we were supposed to find out. I hope you were able to follow this problem and all the 4 steps to solve problems on normal distribution. Moving ahead, and let us solve the last problem of the today's series, that is the problem on Gumbel distribution. Let me read the problem. Analysis of the rainfall records at a rain gauge station reveals 200-year rainfall as 550 mm and 100-year rainfall as 350 mm. The rainfall magnitude for 500-year rainfall at that station, considering the Gumbel distribution, is what we are supposed to find out. Okay, so we are given the rainfall record of 200-year rainfall and 100-year rainfall, which is 550 mm and 350 mm. Now we need to find out what will be the corresponding rainfall magnitude against 500-year rainfall at that same station, and for that purpose we need to use the Gumbel distribution, which is mentioned in the problem. So first of all, let us deduce what is given in the problem. Here x200, that is log transform x, is given to us, that is x bar plus k200 as x equal to 550. Likewise x100 is also provided to us, which is 350. So now let's compare both this equation. So if we compare in the sense, like if we subtract x200 with x100, then we get k200 minus k100 in bracket sx. So further solving this equation, we will reach at this stage that is k200 minus k100 in bracket sx is equal to 200. Okay, but now what is k200 and k100? For that purpose also we can also write these equations, like k200 is nothing but y200 minus yn bar divided by sn, where this sn is nothing but its standard deviation, yn is nothing, it's the mean around the variable y. Likewise for k100 it is y100 minus yn bar upon sn. So for a given data size, which is a very huge data size here, so this n, yn bar and sn are constants. So keeping these all information in mind, let's move ahead to step 2, where we now going to find out the reduced variates of 200 and 100 years return periods. So now we know that n, yn bar and sn are constants in this equation. So now substituting them such that we can find out the y200. So how to find out y200? For that purpose we have this equation minus ln divided by the return period t divided by return period minus 1. So 200 is the return period for the first reduced variate. So 200 divided by 200 minus 1, which is 199, which is obtained as 5.2958 for y200. And likewise we can obtain y100 by using the same equation for 100-year return period, which is obtained as 4.6. Now we can substitute these values in the main equation, that is k200 minus k100 as x is equal to 200, which we have seen in step 1. So here, what is k200? This is the equation that I have written directly, and this is k100. This is the equation for k100 that I have written directly, and multiplying this entire bracket, square bracket, with sx, which is the standard deviation around x. Now if I solve this equation, it is reduced to y200 minus y100 divided by sn is equal to xx. So here we now know the value of y200 and y100, and we also know the value of and we also know 200 here. So rearranging this equation will end up to the value of the ratio of sx by sn, which is 287.4956. So this is what we have obtained. That is the ratio of the standard deviation around x and the standard deviation around y in the step 2. So moving ahead, now let us find out the reduced variates for 500 return period, which is what is the final purpose of this question, step 3. So how to obtain that? So y500, we are going to utilize the same equation, that is minus ln in bracket return period t, which is 500 divided by return period t minus 1, that is 499, which is obtained as 6.21. So now substituting these values in this equation, that is x500 minus x200, so we can write this, we can expand this as k500 minus k200 as x, and we now know what is k500 and k200 is. It can be rewritten as y500 minus y200 divided by sn into sx. Right, so I hope you were able to follow the previous step, and we are utilizing the knowledge that we obtained in the previous step in this step itself, and then substituting the values of y500, y200, and the ratio sx by sn here in this equation. We can substitute them as 6.2136 as y500, 5.2958 as y200 into this ratio that we obtained in the previous step. So multiplying them and bringing this x200, because this information is also known to us, which is already given in the problem, that is 550, and solving them, we obtained x500, which is the final purpose of this question, as 813.862 as the final response. I do understand that this was a very complex and a very lengthy problem. However, if we follow these steps, it becomes very comfortable to arrive at the final response with regards to whatever the unknown and the known things which are given in the problem. So today in this lecture series, we actually solved problems on plotting position formula, log normal distribution, normal distribution, and Gumbel distribution. I hope these problems will surely going to help you out in solving the assignment problems of the NPTEL course on surface water hydrology. Thank you.